everyone, welcome to lecture 25 in physical organic chemistry. In our previous class, we had seen a detailed discussion on the Diels-Alder cycloadditions. Moving further, we will see cycloadditions of a different kind, in which today we are going to see 1,3 dipolar cycloadditions. As always, most of the material in the pericyclic reaction topic has been sourced from Professor Shankaraman's Pericyclic Reactions, a textbook, as well as his lecture notes. Moving further, let's see what are dipolar cycloaddition reactions. Similar to our Diels-Alder reactions, dipolar cycloaddition reactions are thermal 4 plus 2, specifically the 4 pi supra plus 4 pi supra reactions involving 6 pi electrons and an aromatic transition state. And obviously this is thermally allowed. The 4 pi electron components are referred to as 1,3 dipoles, and these are the compounds in which the stable all-octet Lewis structure can be represented by zwitterionic forms, in which the positive charge resides on the central atom and the negative charge is spread over the terminal atoms. Unlike our Diels-Alder dienes, the 4 pi component contains only 3 atoms. Okay, your diene in a Diels-Alder has 4 atoms, whereas the 4 pi component in this class of reactions will have only 3 atoms, of which almost always one of them will be a heteroatom. That means it will not be a carbon. Therefore, the 1,3 dipolar cycloaddition invariably is a method for the construction of 5-membered ring systems in which one of them will be a heteroatom. The 2 pi component is called a dipolarophile and it is usually an alkene or an alkyne. Something similar to this. So we will see a detailed description of what this means. Now a large number of 1,3 dipoles are known and their reactions with dipolar have been studied. Most important work in 1,3 dipolar cycloaddition has been done by Houston, and he classified 1,3 dipoles into 2 categories, the allyl anion type and the propargyl allynyl type. Okay, what is the difference between the two? The main difference between the two is that the allyl anion type have a bent structure, whereas the propargyl allynyl type have a linear structure. In the propargyl allynyl category, the central atom can be only a nitrogen atom compulsorily. We are going to see today the reactions of nitrones, nitral oxides and azomethane ylides. Okay. Very importantly, we had seen in our previous classes, in our previous courses, the reactions of ozone, in which we had described the ozonolysis reaction as being as a 1,3 dipolar cycloaddition, leading to the formation of a monoozonide and resulting in the oxidation of alkenes. So, a variety of dipoles are depicted in this particular figure, in which you can have, as we had seen, azomethane ylide, azomethane imines, nitrones, enzymes, azoxys, nitros, carbonyl ylides. This is a very important class of 1,3 dipoles, and In your higher classes, you will see metal-mediated synthesis of carbonyl ylides and their cycloadditions to dipolarophiles, leading to oxygen heterocycles. You can have carbonyl imines, carbonyl oxides, nitrosoimines, nitroso oxides, and like we mentioned, you can have ozone, in which you will lead to an oxidation of an alkene. In the propargyl allynyl type, you can have nitrile ylides, nitrile imines, nitrile oxides. We are going to see some reactions of these. You can have diisoalkanes. You can have azides. Azides are also very important 1,3 dipoles, leading to the synthesis of triazoles. And you can have nitrous oxides. What is the mechanism of 1,3 dipolar cycloaddition reaction? The 1,3 dipolar cycloadditions are usually concerted reactions, and most of them obey the Woodward-Hoffmann rules. Previously, a stepwise diradical mechanism had been proposed, but these were ruled out by Houston, and on the basis of solvent effects on the reaction rates as well as kinetic isotope effects and the stereochemical evidences. Surprisingly, 1,3 dipolar cycloadditions are relatively insensitive to solvent polarity, contrary to what you would expect for a reaction that has cations and anions involved, or rather dipolar nature of the substrate is involved. One would expect it to be extremely sensitive to polarity effects, but surprisingly, these have been shown to be quite insensitive to solvent polarities. Therefore, these reactions can also be carried out quite well in simple nonpolar solvents. Some of these dipolar cycloadditions are controlled by the HOMO-LUMO gap. You can have the HOMO of the dipole and the LUMO of the dipolarified, whereas in some cases you can consider the HOMO of the dipolarified and the LUMO of the dipole. Both of these type of interactions may be important in most of the 1,3 dipolar cycloadditions. What is important is that the energy gap between one of them will lead to the faster reaction. Okay, so the gap between the HOMO of the dipole and the LUMO of the dipolarified could be smaller, or depending on the substituents, the HOMO of dipolarified and LUMO of dipole may be a smaller gap. It will all depend on what substituents are present at either the dipole or the dipolarified. One very important thing that we have to remember in this is that simple alkenes, which we saw are not very good dinophiles in the Diels-Alder reactions, are now pretty good dipolarophiles along with electron deficient alkenes, which already were good uh, dinophiles, and they are also good dipolarophiles. The difference between the diene and the 1,3 dipole is that dienes are usually nucleophilic because they have very high homos, and because of which they prefer to use the HOMO in the cycloaddition with electron deficient dinophiles. In the case of 1,3 dipoles, 1,3 dipoles are both electrophilic and nucleophilic. They can use either their HOMO or their LUMO depending on whether the dipolarified is electron rich or it is electron poor. Something like this. So you can see here this is a first one is a reaction of an electron rich dipolarified in which the 1,3 dipole uses its LUMO, the alkene uses its HOMO. Whereas if this is an electron poor dipolarified, then it will use its HOMO, and the electrophilic alkene, which is now electron poor, will use its LUMO. Okay, so with electron-rich dipolarophiles, the alkene will use its HOMO, forcing the 1,3-dipole to use its LUMO. On the other hand, if the alkene is electron deficient, obviously it will use its LUMO, forcing the 1,3-dipole to use its HOMO. This will also have a bearing on the regioselectivity. Okay, so depending on which groups are present on R, if R is electron rich or R is electron deficient, the negative end of the 1,3 dipole will accordingly attack that particular terminus which is electron deficient. As I had mentioned, the regioselectivities of these reactions are controlled by the magnitude of atomic coefficients in the HOMO-LUMO levels of the interacting components, as we had seen in the Diels-Alder reactions. The HOMO-LUMO energy gaps and their coefficients of the atomic orbitals for various 1,3 dipoles are already known. Thereby, we know how to predict the regioselectivity in such reactions. Therefore, these reactions are usually highly regioselective, and in addition to this, they are also highly stereoselective. The stereochemistry comes from the best approach with the least steric hindrance. So, one would expect that the most stable product formed, which is relatively free from steric effects, will predominate. There is no endo rule in these cycloadditions as compared to Diels-Alder reactions, simply because there is no conjugating group that can interact across space at the back of the dipole or dipolorophile. Therefore, the products that are formed are most often the most stable exoproduct. Let's now go to the reactions of nitrones. The cycloaddition of nitrones leads to the formation of isoxazolidines. In this reaction, normally you can have the formation of 3 asymmetric centers in one go. And these are the products, the cycloadducts of this dipolar cycloaddition are very useful starting materials in the synthesis of beta amino alcohols, which are formed upon the reduction of the cycloadducts with the retention of chiral centers. That means if you reduce these, okay, all of these, when you reduce this, when you can cleave this particular bond by reduction, this is a heteroatom bond and is relatively weak. The LUMO of these bonds are quite low and you can reduce them very easily, thereby leading to the cleavage of these bonds without affecting any of the chiral centers. How do you generate these nitrones? Nitrones can be generated very easily by just forming oximes with highly reactive aldehydes, followed by a dehydration reaction to give you the nitrone. Or these can be simply oxidized or these can be formed by simple oxidation of hydroxyl amines. Here are some reactions for nitrones. You can see here this bicyclic substrate reacts beautifully well. In this particular case, this is electron deficient. So obviously the negative end will add to the most electrophilic part. So you can very easily predict the regioselectivity in these reactions. And you will find that this has formed the exoproduct. You can see here that 1, 2, 3 new stereocenters have been generated in this reaction. In this particular case, in the second example, you can see a non-polar solvent has been used and this gives a beautiful 1,3-dipolar cycloaddition in which after zinc acetic acid reductive cleavage we have the cleavage of this particular moiety, the NO bond, leads to this beta amino alcohol, and this can now be taken forward in a natural product synthesis. In the third example, this now forms a nitrone with this carbonyl moiety. This is ester, remains unreactive. So now this is an electron deficient nitrone. Nonetheless, it has to form a 5,5 fusion, and the 5,5 fusion is necessarily cis in most of the cases. In very rare cases, this can be trans. Mostly this is cis, okay, because of the strain present in the system. Now you can see here the NO bond can be cleaved reductively either by hydrogen or by lithium aluminum hydride. This leads to the reduction of the ester as well as the NO bond. And in the first case, you can see with rhodium under hydrogenation conditions, only the NO bond is cleaved. The ester remains as such. This is an example of an asymmetric cycloaddition in which a chiral sulfoxide is taken. Why this is chiral? Because sulfoxides are tetrahedral. One of the lone pairs is oriented in one of the corners of the tetrahedron. Therefore, you can actually resolve these, or you can make them in a chiral form, in enantiomerically pure form, and you can react these are very important, sometimes very used as very important chiral auxiliaries. So you can see here this cycloaddition leads to this heterocycle which can now be cleaved reductively and taken forward in several steps in a natural product synthesis. Similarly, you can see here in this the box ligand, the copper box ligand, is used as a chiral catalyst, and this leads to an asymmetric transformation between two achiral substrates, leading to a major of the exo product which is sterically less hindered and an enantiomeric excess of approximately 90%. Moving further, let us see reactions of azomethane ylides. The azomethane ylides react with olefinic and acetylenic dipolar to yield pyrrolidines and delta 3 pyrrolenes. And you can convert each of these to pyrroles. Usually, the azomethane ylides are generated in situ and they are mostly never isolated. See the first example. This is an electrocyclic ring opening reaction under thermal conditions, resulting in an azomethane ylide which now traps this dipolarophile, the alpha beta unsaturated acrylic ester, giving you pyrrolidine in very decent yields. Obviously, the selectivity comes from this negative center adding on to this particular electrophilic end. In the second case, we had seen this example when we were studying electrocyclizations. Okay, so azomethane ylides can be generated via electrocyclic ring opening of aziridines, and therefore you can trap these using dimethyl acetylene dicarboxylate as a dipolar file, giving rise to two diastereomeric cycloadducts, clearly indicating whether the electrocyclic ring opening is thermal or photochemical. Now, aziridines which have pendant olefinic or acetylenic groups, that means the groups that are present in the same molecule, they will undergo an intramolecular cycloaddition reaction of the azomethane ylide. This is very useful when you have to form bicyclic systems that are shown here. So you can see here in the first case, a thermal electrocyclic ring opening of this aziridine leads to a 1,3 dipole, which traps this dipolarified to give you this fused 5,6 fused ring system. Similarly, in the second case, once again, this is heated at very high temperatures to give you a thermal ring opening of the aziridine, leading to a dipolar cycloaddition with the acetylene, thereby leading to a pyrrole which is fused to this six-membered ring system. Similarly, in this particular case, once again, you can have a cycloaddition, again a thermal ring opening of the aziridine, giving you an azomethane ylide, which now reacts with the Z olefin, thereby giving you a highly stereoselective cycloaddition, which can now be taken forward to a natural product synthesis. In this case, you can see here, this is a chiral catalyst or chiral cobalt catalyst using this amino alcohol as a chiral ligand, leading to a highly enantioselective 1,3 dipolar cycloaddition reaction. Similarly, in the next case, you can see this is a silver catalyst and this is a phosphine chiral phosphine ligand, which is C2 symmetric. This, when used in the reaction of this azomethane ylide, leads to a wonderful cycloaddition in very high yields and moderate enantiomeric excess. Let's now see the reactions of nitrile oxides. Nitrile oxides are 1,3 dipoles which belong to the propargyl allynyl type. They also react with alkenes to give isoxazolines, and they react with acetylenes to form isoxazoles, as you can see here in the diagram below. So if you react with alkenes, you get isoxazolines, and if you react with acetylenes, you get isoxazoles. How do you generate nitrile oxides? Nitrile oxides can be generated very easily from oximes, from alpha halooximes, by dehydrohalogenation under basic conditions to give you these linear nitrile oxides. They can also be generated by dehydration of nitro compounds which possess an alpha hydrogen, thereby generating the nitrile oxide. So this isocyanate is used as a dehydrating agent. What is the utility of these isoxazolines? These isoxazolines can once again be cleaved reductively to give you either amino alcohols by a complete reduction, or by reduction and hydrolysis can give you beta hydroxy ketones. So synthetically these cycloadducts are very important. So you can see here in this particular example, this is now a Z double bond, gives you stereoselectively this particular cycloadduct, which can now be cleaved reductively. First you have reduction of this imine type bond, and then you have cleavage of the NO bond, leading to a mixture of diastereomers in a 9:1 ratio and very good yield. Similarly, you can also do a cycloaddition. You can generate, now you see here, this is a nitro compound which has a alpha H. This can be dehydrated using phenyl isocyanate, generates a nitrile oxide in situ. gives you a cycloaddition, 1,3-dipolar cycloaddition on the use of ranitidine and hydrogen followed by hydrolysis. You can have this particular product, which is an aldol product. So indirectly you can generate aldol type products using 1,3-dipolar cycloaddition reactions followed by reductive cleavage and hydrolysis. In the next example, in the second example, once again this is a nitro compound generates an nitrile oxide upon reaction with isocyanate and followed by a 1,3-dipolar cycloaddition. Upon usage of ranitidine and boric acid, you end up getting this aldol type product, which is then treated with benzyl chloride to carry out an elimination reaction, and then one can carry out the hydrolysis of this to give you a natural product. In the next example, this particular natural product is also obtained in several steps from this 1,3-dipolar cycloaddition. So this is an oxidizing agent and generates an alpha chlorooxime, which then undergoes a dehydrohalogenation to give you this nitrile oxide. This now reacts with this dipolarified to give you a 1,3-dipolar cycloaddition. After 5 steps, you can get this particular natural product, which belongs to the guanidine class of compounds. In this particular case, this alpha halooxime can now be dehydrohalogenated and then coupled with this allyl alcohol to give you this particular isoxazolidine in very high enantiomeric excess when diethyl zinc and this amino alcohol derived from tartaric acid is utilized in this particular transformation. So this is the chiral ligand and this is the transition metal that is employed for this particular cycloaddition. In another case, the chiral auxiliary is used. This is called as the camphor sultam. This is now coupled to dipolarified. This now undergoes a wonderful 1,3-dipolar cycloaddition to give you in very high selectivity, as you can see here, 2 cycloidex, which can be very easily converted into amino alcohols, beta amino alcohols using reductive cleavage. So what we saw today is a glimpse of 1,3-dipolar cycloadditions. In our future class, we shall see the theory and applications of sigmatropic reactions. Thank you everybody. We'll see you at the next class. Goodbye.